Hey guys, this is John Michael Hands. Today I'm going to walk you through operating the SNIA TCO model for storage. We built this model from the ground up to be a lot simpler than a lot of data center TCO models, but have all the metrics in there that actually materially affect the data center total cost of ownership for storage. So when you're thinking about the storage total cost of ownership, obviously the cost of the storage, the capex, everything that's in the rack makes up a large chunk of the total cost of ownership. But then there's also the operational expenditures, power, rack space, cooling, any other data center expenses. So yeah, we try to make the model as simple as possible without including every tiny little thing. There's stuff like software licensing or other things you can add in there, but I can show you guys how you would do that. But really just wanted to orient people around the Excel model. We try not to overdo it with adding too much complexity in there. So I'm going to walk you guys through the model. So what you have up top is the drive attributes, and really the way this is structured is basically trying to compare one drive versus another drive or one rack versus another rack. In this scenario that I set up as an example, I'm comparing a hard drive rack for something like a cloud object store, like say Ceph for instance, versus SSDs. And so I got a lot of questions about this, about the defaults in here. It's just meant for an example. You're going to have to put the numbers in yourself. It's a model. The model you give it inputs, and the model gives you outputs. So one of the things you have to model correctly is the drives. So when you look at the drives, you can see here the drive attributes here on the top. You have your drive name. I just named these HDD8, this 8 terabyte drive, and you put the capacity in gigabytes. And then you're going to put the power active and then the power idle. You can get these from the spec sheet. Hard drive spec sheets, you have to make sure that when you're looking at the idle power, it's not it gets a little bit tricky. They have this thing called idle B, which basically it's where they can park the heads, but the motor's still spinning, and it gets down to about 3 watts for a typical enterprise 7200 RPM drive. But you kind of have to know some of the power attributes of the devices you're modeling. But for the most part, you can just go look at the spec sheet, look at the idle power, look at the active power, and pop them in here. The AFR, the annual failure rate, you can model whatever. I put in 1.8% in this test. That was like a backblaze number that we had seen previously that they reported kind of for the average over a couple of years for hard drives. Most of the modern hard drives, are rated at 0.35 or 0.44% AFR. AFR and mean time between failure are the exact same thing. So a 2 million hour mean time between failure corresponds to a 0.44% AFR. And so you can just do that math. And you'll see when we actually look at the math of how we calculate the number of failures, we actually use that conversion because we're going to look at the total number of drive hours. So if you were to just look at the spec sheet and you look at the spec sheet and it says 2 million hours, you can put in 0.44% here. And again, this is a model. It's meant to be changed. It's meant to just be comparing A versus B. Some scenarios where if you're in a data center that has higher temperature, humidity, or you're running the hard drives past their rated workloads, maybe they will have a higher percent AFR. So you have to kind of understand some of the workload environment. But the most important thing for the TCO model is the price. So if you look at the price and the ASP in dollar per gigabyte and ASP just for the unit, the way I have it modeled here is you just put in the dollar per gigabyte, and you can usually find this from IDC. You can go on Newegg and look at what the price of a hard drive is and divide it, by the capacity to get the dollar per gigabyte, and then it will give you the average selling price of the drive. Again, I just put 2 cents in here for the model. The hard drive prices change very frequently depending on supply and demand, and over time they generally go down. That's what we've seen in the last couple of decades. So it's safe to say when you're looking at these models, you're going to have to look at what the costs are for your use case. And so basically for every single column, you basically have a different type of drive. And in here I have the gray, the gray ones, which are the hard drives, and the blue ones being modeled by different racks. So the drive input is over here. The other input you have to do is the rack and system. So this is the rack TCO. So if you look at the rack, and I can expand this here a little bit, but you basically have data center cost and rack space. So you could do this by month, or you could do this over the course of the whole 5 years. Basically, the way we have it set up right now is it does it for the whole deployment term, and it basically we'll amortize that over this. You can kind of look at a rack cost. So maybe if you're in a co-location and they charge by the month for square foot, you can put that in. There's some very easy ways to go do that. But for the most part, we're just trying to compare A versus B. So if the rack is, if the data center costs are staying the same. Now, obviously, if you're going to a smaller deployment and you use less racks, then that's going to be a material impact for the data center TCO. But you'll see when we walk through some of the things that majorly affect it, that's not one of the major drivers of TCO in storage. It's really about the cost of the storage and the replication factor and that you choose for the storage deployment. But so you would come in here and you model a server cost, a JBOD, a switch, everything that's in the rack that it is not the actual storage itself. And then you basically can model the number of rack units they have and the number of power that they take. So I'm just guessing, okay, this server takes 450 watts. Again, this is something you're going to have to go model yourself. A standard data center server takes anywhere from 400 watts to 600 watts, depending on kind of the CPU TDP. You're going to have to go play around with that. And then JBOD power, I put 250 watts in here. A more energy efficient JBOD is more like 70 watts for hard drives with a single expander type model. The higher power models with higher 90 bay type JBODs are going to be a little bit higher power. So you're going to have to just look at the spec sheet. So what this does is basically it takes the Capex cost per rack. So I'm just summing up basically everything in the rack, and I'm doing that for the HDD rack, and then I'm doing it for the SSD rack. And the HDD rack is going to use the gray, and the SSD rack is going to use the blue. And then you can put in here constants, electricity cost, and then data center power usage, effectiveness. So maybe if you're basically just looking at A versus B and you're in a colo, you're basically saying, okay, well, I'm getting, basically really good efficiency 1.1 because you're basically just losing the efficiency of whatever the conversion is at the actual power distribution unit level. If you're running your own data center, you're going to have a higher PUE because you actually have to factor in the facts of cooling and other stuff into that data center cost. So remember, the data center PUE is the total power that went into the data center divided by the actual power consumed by the IT equipment. And then the drive replacement cost, typically drives are under like a 5-year warranty. So if you if a drive fails, you don't really have to pay for the free cost of the drive, but you do have to pay for a technician to go out there. Generally, professional services for like a co-location is going to be like $150 or $200, something like that, to go send a technician out to a server, find a drive and pull it and replace it or something. So you can put in whatever you want here. So the most important part of the entire TCO model is going to be this workload section. And I tried to keep it really easy with the numbers, but it requires some explanation. So the first is the deployment term. So you're going to look at the total cost of ownership over a certain number of years. And this is going to impact obviously the number of drive failures, because the longer you run the hardware, the more chance of failures. It's going to impact the amount of power you consume. And we're going to normalize that per terabyte and per month so that we can kind of amortize all the equipment out that you cost. So the longer you're doing the deployment, then the money you spend up front, you get to use that and amortize it over a longer period of time. So a 5-year deployment is pretty typical, but data center deployments range from 3 to 5 years. So error encoding and replication. There's 3 tabs in here. There's a RAID 5 overhead, RAID 6, and an erasure code. And you can depending on what you pick. But say for instance, I picked a 4.2 erasure code. I would go 4.2. So that means 4 data, 2 parity. That would be a 1.5 overhead. And so if you go back to the TCO, I'm comparing, in this case, 3 means 3x copies, so that's a triple replication. This is very, very common in object stores like Ceph today with hard drives because of blast radius concerns, that they either duplicate the data with a mirror or they actually triple replicate it if it's a larger deployment across different servers and different availability zones. And for the SSD, I put 1.5 here. This is kind of a fun example. We're trying to say, okay, how do we make SSDs TCO kind of look better than hard drive in this case? Well, if you use erasure code with SSDs, then you can basically get all the IOPS, all the performance, and but you can use a much lower overhead and still have a good rebuild time and blast radius and all this stuff. So there's in this error encoding and replication, if you're not using a constant factor between the comparison, then you kind of have to explain why. I mentioned in this case, I'm just basically making up an example where I'm comparing equivalent durability, so the durability of triple replication versus the durability of having a 4-2 erasure code with 2 parity shards, these are the same or equivalent durability. Actually, the SSD is probably better durability because the rebuild time is lower. But I'm saying this is going to be a lower cost. Now, this is really impactful because when you look at the Capex per TBE, so this is a very important, in the white paper, we talk about terabytes effective or effective capacity. So when you're looking at the total cost of ownership, you don't get to look at just the raw number of gigabytes or terabytes in the rack. You actually have to look at how much usable data you can store in that rack. And this is called terabytes effective or effective capacity. And so obviously, if you have something like replication, it's an easy example. If you're copying your data once and making a backup like a RAID 1, then you've doubled your cost of storage. It's costing you 2 drives worth of data to store 1 drive worth of real data, user data. And so this error encoding and replication actually has a material effect on the TCO because it's a multiplier. Anything that's a multiplier is going to be a massive impact on TCO. So the performance one, there's a million ways to do this. There's people that make IOPS-based TCO models. We have one that's bandwidth. I have ones we made for cloud service providers to model different types of IOPS per terabyte for different cloud workloads. But this was supposed to be an easy way to just say, okay, if workload A versus workload B, if you're buying more drives than you need because to hit an IOPS target, then this performance multiplier is just what's the ratio of how much more storage you're buying or over provisioning basically compared to the baseline. So if I said, okay, in this case, I'm actually already doing 3 copies of the data, so I just left the performance multiplier at 1. But say, for instance, we wanted to just say, okay, we're only going to have a mirror across all the storage across HDD and SSD, but for hard drives, they're not quite fast enough, so we actually have to buy like at least 1.5x more storage than they need to hit an IOPS target. But for the SSDs, they can reach an IOPS target without doing that. Then I would put an overhead here of 1.5. So it's really a relative thing. This performance multiplier is you're looking at when you're comparing one rack versus another rack, or one deployment versus another deployment. It's really a comparative factor. And this is supposed to be kind of an easy way to think about performance instead of trying to like model these specific IOPS for each workload, because you can do that, but it's going to be a lot harder to understand, because if you look at a performance-based TCO model for SSDs, well, SSDs always win because they're 1,000 times faster than a hard drive. So, nobody would be buying hard drives if that were true. Obviously, people weight performance a little bit, but they also weight cost and other things, power and cooling and utilization. The other thing, capacity utilization. So say, for instance, you always wanted to keep 25% free space because of making sure that you have buffer for new deployments and new workloads. You would put something like 75% here because you're trying to keep the capacity at a certain utilization rate. And again, this is in the comparison. People might not like that I put 75% for the hard drives and 90% for the SSDs. Just change it. You can change it. It's if you put 90% across the board, you can do that. So the duty cycle, active versus idle, this is, again, depending on your IOPS and workload. So if you have a drive busy time, so if your IOPS per drive on hard drive is like, say, 200, then your drive's going to be really, really busy. It's going to be 70% or 80% busy. But on an SSD, that same number of IOPS would be very, very low utilization for an SSD. So it would spend more time in the idle power. And again, when you look at an SSD idle power today, a typical data center NVMe is between 2 and 4 watts idle power, and then like 15 to 25 watts for U.2 active. So it's a really big deal, depending on like actively modeling what the duty cycle of the drive is. So that, again, we use this duty cycle percentage to actually calculate the power, because we look at over that 5 years, how much time does that drive spend in idle versus how much time does that drive spend actively doing I/O. So if you look at that, you can use the duty cycle to think about, basically, how much percentage of the time is the drive being used. The last thing we're going to look at is, for the workload, is the data reduction ratio. So this is compression factor. So if you have compression or dedupe, and so, again, one of the things we look at for hard drive versus SSD is, say, for instance, you can enable compression on the SSD because you have surplus IOPS, and you get a 2-to-1 compression ratio. So you're kind of using text or some kind of compressible type data, even like if it's like a a messaging app or something where there's like a 6x compression ratio. So you can model that in here just kind of at a ratio. So if I get a 2-to-1 compression ratio on my storage, so I'm storing twice the amount of data in that storage versus the actual storage used. I'm getting a 2-to-1 compression ratio. I would put a 50% in here. And for SSDs, if you look at the terabyte effective for how these, like a storage array vendor or any of these guys that are selling storage systems, look when they say, oh, it's a 5 petabyte server, they're actually usually talking about after compression, after dedupe, after this data reduction, because they're giving you more usable capacity for the same physical capacity. And this ratio is going to be heavily dependent on the workload, the type of data, and the customer. When I talk to these major storage vendors that actually measure this, they actually have tools for the customer to measure their data compression ratio on data reduction ratio based on these storage subsystems, for each workload. So then this is just one more knob, but the workloads are actually as important as the price, because you can have massive multipliers in these workloads that materially affect the TCO. So those are the inputs. You have the drive attributes, the workload, and the rack and system, and the fixed costs. Now you go to the calculations, and it's fairly straightforward. When we go look at the Capex is the blue, so capital expenditures. You just look at how much capacity you are getting per rack. So I just basically take the number of drives and the number of JBODs per number of drives per server, number of drives per JBOD, and then how many per rack. And then you're looking at a per rack metric of like how many terabytes do you have, and then your capex of storage is basically like how many terabytes are you storing times the dollar per gigabyte of the storage, and then the capex of the rack we're just getting from over here, which is basically the sum of all the other stuff in the rack, like the servers and the JBODs and the cables and the connectors and the cost of the rack itself, and then we're giving a total. And then when you have that total, you can divide it by the total number of terabytes to get the capex per terabyte raw. But I mentioned that's actually not the really important number. The really important number is this capex total per terabyte effective, which is the effective capacity after all these multipliers and the error encoding and replications. How much is it actually costing you per terabyte effective to store the data? And in this case, with an 8 terabyte hard drive, with all these stuff I put in here, it's costing us $108 for the lifetime of that storage per terabyte. And then if you divide that by the 5 years, we're paying $1.81 per month. And remember, so everything in the rack matters, everything on the storage side matters. The capex per terabyte effective is basically all the stuff, all the capex, storage, hardware, and then you amortize that over the amount of deployments, because in a storage-based TCO model, what you care about is how much data you can store at what cost. The next part is easy. It's the Opex. You're basically looking at how much power does this rack consume. And so when you look at power storage, active versus idle, remember we're using the number of drives and then the duty cycle to calculate actually how much power the storage is consuming. And then this power max is really just the rack limit with the max. Basically when data center operators are speccing a rack for the power distribution units, they're looking at the max power that rack will ever consume, not the average power. So this is just kind of a nice metric for if you're looking at like how much storage can I fit in this rack. So this SSD deployment that I modeled is kind of silly, right? We're looking at like a 26 kilowatt rack. Anybody who's built a real rack knows that this is very, very high power for a single rack. But it's not maybe out of the question for like a large hyperscale data center that are with the most modern rack technology. But it's just a fun comparison. So remember, you got to put in your own data in here. And this is just an example, the one we download. And then, okay, so now that we have the total amount of power that in watts that this rack is going to consume, we know the Opex of storage because we just look at the cost of electricity and then the power usage effectiveness, and we can calculate the amount of electricity cost over the 5-year deployment term, and then we can amortize that over per month. The other thing we're going to look at is Opex of drive failures and replacements. This is, again, basically taking the annual failure rate and looking at the total number of drives, and you're saying we're converting annual failure rate to mean time between failure in hours, and then we're multiplying the number of drive hours times the deployment term times the number of drives, and you have the total number of drive hours in millions of hours. And then you divide that by the actual amount of failures. So if it's one failure for every 2 million hours, then you actually know precisely how many drive failures you're going to have over that 5-year deployment. And then We just basically take the cost of, okay, if it costs $300 to send a technician out there, how much are you going to pay over that deployment term for drive failures? And then that's it. We just sum everything up and then amortize it again at terabytes and then terabytes effective, just like we did above in the Capex. And then you're actually going to have the effective capacity for your Opex per month. And then the bottom here is just a summary. So now you can start comparing, and I just graph it over here. And sorry, we'll have to scroll over with the way I have this uh, set up. I'll have to scroll over here real quick. Okay. So now we have on the bottom the summary, and you can kind of see there's that one graph that just basically breaks out by percentage the TCO per terabyte effective of Capex versus Opex. You can see like in this, the smaller capacity hard drives have a much larger percent of Opex. That makes sense because you're amortizing the same equipment over a smaller amount of terabytes. You have more drives, they're less power efficient as far as like watts per terabyte. So that would make total sense. SSDs are much more power efficient than hard drives. So you can see the Opex is going to be a lower percentage of the TCO. And then you have the TCO in actual real dollars, because at the end of the day, that's what matters. And in this fun example, I have a 30 terabyte NVMe kind of coming close to an 8 terabyte hard drive in TCO per terabyte effective. But this is how somebody would use this type of TCO model in a real deployment. We worked with many cloud customers showing them this model and kind of looking at does this make sense? We talked to many, when I was making the model, I talked to many different groups at Intel, like the Ceph group, the CDN group, all these people that have all kinds of different data center workloads, and we vetted the model with them. And so I hope you guys find this helpful. Again, if you have any questions, I'm John Michael Hands at SNIA. You can find me, and we'll go from there. We can have a deeper dive sometime with another case study. Bye-bye.